Dear student, Assalamu alaikum. Welcome back to online physical chemistry course 2. The topic of today's lecture is Eigen and non-Eigen function. In this lecture, we will discuss Eigen and non-Eigen function and application of Eigen function in quantum mechanics. The book which I follow for this lecture is Advanced Physical Chemistry, written by D.N. Bajpai, and Physical Chemistry, written by Era N. Levine. As we know, different terminology is used for quantum mechanics. So Eigen function and non-Eigen function is one of the terminology, and we will discuss this terminology in this lecture. When operator operate on function, it gives same function with the some constant value, then this particular function we will call Eigen function, and the constant value which we obtain is called Eigen value. So operator operate on a function. Function is any variable like time, wave function, momentum, etc. So when operator on this function, it give a constant value and same function is repeat, then we will call this phenomena. This phenomena follow the Eigen function phenomena. When operator operate on a function, it does not give the same function as a resultant. So the particular function we will call non-Eigen function for particular operator. So this will be, if it not is equal to the same function, this function after operation we will call non-Eigen function. Now we will take the example whether this operator will be a particular operator will be Eigen function or not. For example, here we apply a derivative operator on a function e raised to power ax and e raised to power ax square. So we want to determine whether this function is a Eigen function for the operator d over dx. We take a supposition that this e raised to power ax is suppose is equal to psi. Now this psi, when operator operate on this psi, operator here is the derivative operator, so it gives the same function and some constant value because the derivative of this function same function, and we will take the power of the power of this function. So it give a and dx will be cancelled. We will obtain a raised to power ax. So a and e raised to power ax, we suppose psi same function is repeat. So we can say that e raised to power ax is the wave function, Eigen function for the operator d over dx. Now if we take the derivative of the e raised to power ax square, it give the value if we take the derivative of this function. So first of all we write this function in the same way as it is present, and then take the derivative of the power. So the derivative of the power give 2ax. Now 2ax is not constant value, that's why that function is not Eigen function for operator d over dx. So this is non-Eigen function. Similarly, we have we know in the quantum mechanics psi is equal to sine kx for the waves. So k is the constant, x is the displacement. Now if we take the double derivative, this is the operator double derivative operator on the psi value, so it give a minus kx square sine kx. So this is the constant value and same function again repeat. So we can say that the sine kx is the Eigen function for the operator del square over del x square. If we write the whole equation, operator operate on a function and it give Eigen value and same function, this whole equation we will call Eigen function. In Eigen function equation, the wave function will be not affected, they will be again repeated. In Schrodinger wave equation for three-dimensional box, we know that curly square psi over curly x square plus curly square psi over curly y square plus curly square psi over curly z square is equal to minus 8 pi square m over h square e raised to power e minus b psi. So psi have this equation have many solutions for the psi. However, those solutions will be acceptable in which psi have finite value and single value for all the coordinates. Similarly, psi should be continuous for all the coordinate, and its integration between the whole space from minus infinity to plus infinity give a finite value, then this psi value can be acceptable, and this psi then if we will call well-behaved function. A well-behaved function here, when operator operate on this well-behaved function, it will give a eigen. It will be the eigen function and will give eigen value. For example, if operator of energy operate on this function, this well-behaved function, it will give a energy value, energy eigen value for this behaved function. Now, as we know that for each physical observable, for each property in the classic mechanics, which we know there is particular a specific operator is present in the quantum mechanics. For example, we have Hamiltonian operator. When operate on a wave function, it gives energy for that particular psi. Well-behaved function psi have energy. We are doing energy calculation. So when operator of Hamiltonian is operate, it will give the value of energy. Similarly, when the momentum operator h bar over I d over iota d over dx phi, when this operator operate on a phi, it give a value, eigen value for the momentum function. Now, as we know, one of the application of the quantum mechanics, that for any measurable property A, when operator A bar operate on this A function, so it give only one eigen value. It will give only one eigen value for particular eigen function. For example, we determine the total energy of the system. So when the energy operator operate on a psi, it will give energy for the psi. So this is the terminology of eigen function used in the quantum mechanics. Thank you very much.